So in this lecture, we're going to talk about three mean squares. So in our previous example with the students who were studying, and we saw their quiz grades and the relationship between their quiz grades and the hours of TV that they watched, we found we had a mean square error of 18.75. But like that number doesn't really mean anything on its own. In regression, we use the multiple mean squares to compare models to each other. So we need some sort of null hypothesis in order to compare this model, right? What's usually the null hypothesis in statistics? Well, it's that there's no relationship. So we're going to use the null hypothesis of no relationship as an alternative model in order to compare our mean square error with another mean square. Now, if there's no relationship, then the only information we have about this data set is the mean of y, which is what their quiz grade was, right? And we remember that their quiz grade was a 5. The average quiz grade was a 5. So we can draw a flat line here at this value of 5 in order to say, okay, in absence of any other information about how much TV they watched or whatever, we can just guess that each person had a quiz grade of a 5. All right, so there's our mean square that is associated with this flat line. It's the mean square regression. And what the mean square regression does is it compares the predicted values, this line here, with the alternative model, which is the mean of y right here. And you can see that in our equation. Y hat is our predicted value, y bar is our mean of y. What we do is we take that distance, we square it, we sum them all up, and then we divide by p minus 1, p just being the number of variables. Okay, so let's take a look at our example. So for this person over here, even though they scored a 10 on the quiz, we predicted that they would score a 7.5 on the quiz. So if we compare that to the mean, which is a 5, then the error term here for this person is a 2.5. This person, their predicted value was a 5, and the mean of y is 5. This person was perfectly average, so their error is a 0. Now let's take a look at this person down here. Note that the actual value, what the person actually scored on the quiz, does not matter at all. What we're looking at is what did we predict for them, which was a 5, and then what is our alternative model, this flat line, predicting for them, right? So that's also a 5. So even though this person's actual value is really off of both of these lines, their error for this calculation is 0, because what we predicted and what the mean of y is are exactly the same for them. And then for this person over here, we predicted that they would score a 2.5 here, and the mean of y is a 5, so the error is a negative 2.5, even though their actual score was a 5 over here. All right, so the mean square regression is about comparing our predicted values here with this alternative model, not taking into account the actual values. So if we take all those error terms and we square them, and then we added up all those squares, we would get a 12.5. So for this data set, our mean square regression is a 12.5. Great, now we have something to compare to our mean square error. All right, we're just looking for the smallest number. So which model has the smallest average error? Our predicted values right here, or a line that's just drawn at the mean of y? Well, it's probably pretty obvious in that our line that we drew at the mean of y, this flat line here, 12.5 is smaller than 18.75. So actually, our mean square regression is showing us that when we just draw a line right here, this minimizes the error with these values better than this fit line that we tried to draw. All right, so summing up, basically, we're comparing the mean square regression and the mean square error to determine how well our line is fitting to the data. So better models are going to have a smaller MSE, which is the predicted values, compared to the MSR, which is the alternative model, that flat line. In this case right here, our MSR was smaller than our MSE, so that's not a good thing. Well, we usually want the MSE to be smaller than the MSR. We can also get another number here, which is the ratio of MSR to MSE, and that's the F value. So if we divide our MSR by our MSE, then we can get a value of F, and usually a bigger number is going to be better, right? We'll see F again a little bit later, but just to show you that's where it comes from. All right, so I said there were 3 mean squares, right? So the third mean square is just mean square total. There's 2 ways we can calculate it, right? It's just the MSR plus the MSE. Another way to think about it is it's the difference between the actual values and that mean of y. So if we took each point and we subtracted where they actually were from just a flat line, squared all those errors and summed them up and then divided by the number of observations minus 1, we would get the mean square total. So in this case, our mean square total is 12.5 plus 18.75, and that's 50. So those are our 3 mean squares. Just to summarize, our mean square regression plus our mean square error equals our mean square total. Hey, does this formula look kind of familiar? It should remind you of the linear model. We're taking a model, we're adding some error, and we get a total. Here is a summary of how each of those mean squares are calculated. And then here's our F value, which again is the mean square regression divided by the mean square error. So our mean square regression and our mean square error give us a way to compare the models that we get. Right? When we get a slope for a line, we can say, okay, there's some error in this slope, but how big is that error? How much of a poor fit do we have to our model? And by comparing the mean square regression, which is just a flat line, that gives us some baseline to say, okay, well, our fit line is actually a good fit or not.